Hopefully this is an opportunity just to enjoy not doing a ton of diligent work at the moment and just sitting back and listening to some software talk. So, so the objective of these sessions for this software primer, and I've given this to some other people, both inside and outside of AppSci, is to kind of take you from 0 to I don't know. I was gonna say 100, but like as fast as
5.
0 to like middle of the road of like
Yeah.
at like a concept level. It covers everything from, we're going to start in kind of hardware land because computers are actually just hardware with electrical signals. And then we're going to move up into, software abstraction, software languages, etc. And we can even take it further than I have notes here for over time, kind of as far as you want. But there are some fundamental things that computer scientists learn and computer engineers learn when they go through school. But if you haven't gone through one of those degree programs, you're probably not familiar with all of these intimate details. Some things may be repeat for some of you, but hopefully it ends up being helpful. So, and I have these all written out, but I think I have an ability to. I used to have an iPad when doing this, but I lost my pen. So draw.
It's so hard to draw with the mouse.
Got it. One, two. Got it. Does that work? Let's see here. Okay, so that works. So we start here with modern computer hardware architecture. This is known as a von Neumann architecture. I don't know if any of you have ever heard of that before, but it's von Neumann's a guy who built basically the conceptual model for how all computers run today. 90% of computers run this way today. And it basically involves like things like short-term memory, CPUs, and then long-term memory and storage and peripherals. And so that's what we're going to kind of go over here. Have you guys ever built a computer before?
I have not.
Like by hand or anything? Jason, you ever built one? You may not be.
I think he said he's doubling meetings, so ignore him right now.
Gotcha. So if you build a computer, you actually physically get usually these components and hand install them yourselves. At the base of a computer, if you will, this blue line that's going around the outsides, that is your motherboard. So it's like the chip, the backplane of the computer. And if you look really closely, there's all these intimate wires that are running through the computer. And those are basically carrying electrical signals between different devices. You can think of that as like, if you ever had Legos, like a Lego set, and you remember the like flat plate they give you to like build a house on top of, it's kind of like a flat plate. And from that flat plate, then you start to put like your car and your house and your swing set and things like that on the flat plate. So that's kind of the backplane of the computer. Then you have 4 key components that are kind of critical to understand. There's variants of these, but for the most part, they're all pretty similar. You have short-term memory, you have a long-term memory, you have central processing unit, and you have GPU, graphics processing unit. We'll start here with the CPU. You can think of the CPU as the brain of the computer. You probably heard that before. And CPUs are really good at doing basic plus or minus calculations. That's like what they were built for. So all of your general computer processing, opening Microsoft Word or like typing in Google, like all of that is handled on the CPU. Then you have the sister of the CPU, which is the GPU. And the GPU is really good at triangle calculations. And its hardware is optimized for those type of calculations. And why is that important? It really is important because graphics processing happens more in like a geometric triangular space. And so it's really good at like complex geometry. and significantly faster. So if you've ever tried to run graphics programs on CPUs, they're slow, they reduce your frame rate, they're not great. GPUs are much more oriented for that. But GPUs kind of suck at the basic plus or minus calculations. So that's why we kind of have those two different hardware sets, and they're distinct in most computers. Now, certain computers for CPUs have integrated graphics. So the little piece of the chip inside the CPU is actually to do some graphics processing and what they call shader calculations, which are those geometric calculations. But for the most part, it usually happens on a GPU. Knowing that 90% of the calculations happen on the CPU, it's probably more like 99. The plus or minus calculations, knowing that that's the brain, how does the brain work? Well, the brain works on something that's called a clock cycle. You can see this little arrow representing a clock cycle. And clock cycles happen at like gigahertz and megahertz levels. So very fast. And basically, it is a signal loop that's happening inside of the CPU. And if you think about what a CPU is, it's a silicon wafer, a layered silicon wafer. And at the lowest level, it's a bunch of on-off switches, transistors. So when a signal runs through there, it's kind of like flipping a series of light switches that go chink, 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 chink at these megahertz cycles. And the reason that that's important is because computers talk in binary, ones and zeros. So when you flip off those light switches, they represent new ones and zeros, basically. We'll get into binary a little bit later in the lessons. That's as far as I'll go for that for now. But CPUs are like flipping off all these light switches, and then they're running on a clock cycle. So that's consistently running even when the computer is not doing anything. The CPU is just running on a clock cycle. And that's where you hear the term overclocking. You can overclock a CPU. So does a GPU. A GPU also runs on a clock cycle, and you can overclock a GPU, basically meaning you're forcing the voltage up to make it run faster cycles. Then you have this thing called random access memory. You may have heard of RAM before. RAM is basically super fast short-term memory, meaning when the computer is shut off, the RAM memory just disappears. It does not save anything. But it's very useful for running programs because it reads and writes very fast. It's what's called volatile memory, if you've ever heard someone say volatile. And then you have your long-term memory. And this usually takes the form of one of three things. It's basically a hard drive, but it's large storage and it's persistent instead of volatile, meaning when you go in and you set the transistors like one specific way, then it's considered stored. It's storing the binary data, and it doesn't disappear when you turn off the power. In the old days, hard drives are mostly disk drives. So if you remember back in the day when you had computers and you turned them on, you heard them start to spin. That's because they had disk drives in them. And they were literally spinning super fast. And there was a little needle on the end of the drive that would spin around a disk like a record player. And that needle would send in like electrical pulses to flip the transistors to store binary code in the hard drive. And that worked for a long time. They're actually probably pretty hard to get now because technology's moved so fast from like 10 years ago. In like the 2010s, they came out with solid state drives, and those were solid state memory, which was slightly different. Still on-off switches inside of it. And I don't know all the details down to the material level of how these work, but the bottom line is that they were basically, the signals would write to multiple areas at one time. So they're significantly faster. Rather than writing a binary line with spinning, you're now writing super fast. And just to give you an idea, hard drives were 20 megabytes. And solid state drives would write at 10 gigabytes or something a second. It was significantly faster. It was like an order of magnitude faster. Well, in very recent years, call it 5 years ago, you started seeing more M2 drives emerge, which are NVMe or M.2 drives, and they look like a little chip. This is, by the way, this had the same SATA connector that this guy did here. So like a SATA connector like connects you into the motherboard basically, and this connects into the motherboard. We'll get into that in a second. This has basically looks like a flash drive almost. It's not quite the same thing, but it plugs into the motherboard, and it's significantly faster than this even. And it's like, I may have these a little bit wrong, but I'm not that far off, like 50 gigabytes a second. So it reads and writes significantly faster. And really, it's just a solid state drive that's compressed down and made way more efficient. Any questions so far? Because I'm going to go into even more details here. But
no, I'm following so far.
Cool. Try to remove some of those notes there. So a lot of days when computers are sold now, they're sold with M2 drives. Solid state drives are sometimes sold externally, so you can plug them in. You might ask the question, like, what is a flash drive? A flash drive is basically a hard drive that's compressed and just fits over a USB port. So it just plugs in with the USB port. And it's external, not inside the actual computer itself. And you can get passport drives and all those same things. They're basically all these forms of storage just compressed into a little USB form factor. And then the next piece that I haven't talked about, and I'll talk about how this all interworks from start to finish here in a second, but the next thing that we haven't talked about is peripherals. So everything that is not one of those components I just mentioned, but gets plugged in over a USB, like your mouse, your keyboard, your camera, your microphone, your headphones, are all considered peripherals for the computer. And the way that peripherals communicate with a computer is over a piece of software called a driver, where basically you click something, there's a transducer from your mechanical action into an electrical signal, which then heads into the computer. It then, over USB, it then hits a piece of software called a driver, which then goes into your operating system and makes something happen. We'll talk about that a little bit more in detail as we move forward. But so that's kind of what's happening at a signal level. There's also, or what I want to do now is I want to talk about what happens at from boot. So like when you first start a computer, like how does everything start running? There's this piece of software that is read-only, that is stored on the motherboard itself. So not on in RAM or in the hard drive, but actually on the motherboard. And it's a very small amount of code, and it's called the BIOS. I don't remember what BIOS stands for, but you've probably heard of that before, like boot into the BIOS and do something. It controls a few basic functions of the like motherboard layer. So you can like turn off, disable camera at like the motherboard layer, for instance. Usually relevant to like laptops. It's more integrated. Or you can turn on things like hardware encryption if you have like a hardware encryption device on the actual piece of or on the actual motherboard. Or you can choose which operating system to load into. So when you click the button on your computer, what happens is you click a button, and that button connects a circuit, which sends a signal down to where the BIOS is stored. And it triggers that BIOS software to run on a clock cycle on the motherboard. Like the motherboard can do like a very basic, or it pulls like the BIOS. It uses the BIOS information stored in that read-only memory, and it starts doing calculations with the CPU. So like if you don't have a CPU, nothing will run. But if you have a CPU, you can run the BIOS at a basic level. And RAM. Sorry, you don't have to have anything else, a CPU and RAM, and you can run the BIOS at a different level. So what happens is that signal goes down, it pushes the BIOS, or it starts the clock cycle of the CPU. The CPU draws the BIOS information and throws it into RAM, random access memory. So it happened, like what I used to say is like button here goes here, or sorry, button. I always get this wrong at the signal level. There we go. Button here goes here. This grabs that information, starts running a clock cycle on it, pushes it into random access memory, and then this starts to run a cycle between CPU and random access memory. That's similar to how an OS actually works. I know that was a little bit confusing, but does that make sense? Because you're always grabbing software, pushing it into memory, and then having the brain of the computer just kind of like check for like inputs from the human and what the software needs to do.
Yeah, that makes sense.
Awesome. Okay, so that's happening in the random access memory. Then from there, the BIOS actually automatically boots up the actual operating system, like Windows. You may ask, well, where does Windows come from if the BIOS is stored here? Windows comes from your hard drive area, your long-term storage memory. So once the BIOS is loaded, if you don't like hold F and load into the BIOS, the BIOS will automatically select like the top hard drive, basically, that has an operating system installed on it. And it will take that operating system then, and it will, the BIOS will be like, hey, go get that operating system and load it back up here. And so the CPU will be like, got it. It'll run through, grab all of those ones and zeros, transport them up through the clock cycle into random access memory, and then load it. And once something is loaded on in RAM, you may ask, how does it display on the screen? How does it get to like the screen itself? Well, if I have a monitor over here, it's plugged in through a USB or HDMI somehow into the motherboard. It could be one of many different connectors, DVI, HDMI, VGI, etc. But it's plugged into the motherboard. The random access memory, the CPU is actually doing this. It's saying like, hey, I'm going to grab this information. I'm going to go through the signals on the motherboard, and I'm going to connect here, and I'm going to pump the pixels that I am supposed to display onto that display from the BIOS software or the operating system software once the operating system starts loading. So when Windows loads up, that's what's actually happening is your CPU is grabbing stuff from random access memory. It's sending it to the display for you to see visually. Okay. Any questions there on like the signal pathways?
No.
Okay, cool. Almost there. It's taking a second to go backwards. Okay, so those are signal pathways. What's happening, or what else is important to know is some more details about these individual devices. Let me see if I talk about this. I talk about CPUs there. We'll get to that. Let's talk about random access memory real quick. Random access memory has these things called like page frames, which are basically like the blocks of storage that it has. And I can't remember a ton of details, but if you want to do reading on it, it's basically the thing that enables it to be so fast.
Okay.
And you may also ask, if random access memory is so fast, why don't we use it for long-term storage? Well, part of the reason it's so fast is that it doesn't have persistent storage. And that's kind of why. Now, there are exceptions to that. There are some RAM systems that actually you can dedicate as persistent memory. They're not meant to be that, but you can. But the goal in the past life was that, this is kind of like getting back into older days, but like random access memory was fast and it was expensive and it was small. So it would be like, you might have like 120 megabytes. Nowadays, you might have like 16 gigabytes, but you can buy RAM sticks and motherboards that support it that are like 240, gigabytes of RAM. And then people can actually store applications in there and there's almost no load time. That's rare that people do that, but I've seen some people do it. But in general, it was really small, and this was really big, but slow. And so you wanted to be able to move fast in your computer, but store long term. And that's why we've had that kind of exist for a long time. Now, M2 drives are so fast. They're not RAM fast, but they're fast. That like we're getting to the point where I don't know if this architecture will maintain the same thing long term. Like if random access memory just gets a little bit further in technology or M2 gets a little further in technology to where they can meet, it may just be a single storage memory system in the future. But it's not today. They still keep them separate. All right, we got another 7 minutes here. So let's back up here. This is your basic, von Neumann computer architecture, pretty standard. Any questions on this before I jump down into details of like CPUs?
No, I'm good on the basics.
Cool. Every piece of computer is pretty similar to that, almost all of them. So CPUs. CPUs are important to know a little bit more detail about because it's worth knowing. You may have heard this before, like 4-core, 16-core CPU, etc. What that really is representing is that a CPU is made up of individual CPUs within the CPU, like individual computing units called cores. And you can use like core 1 and 0 of core 2 or vice versa, or you can split between the two. And that gets into multi-threading and parallel processing, which I'll talk about in a second. But the thing to note for now is that there's lots of cores. Most CPUs come with 4 cores at minimum, at the high end, 16 cores. And then in addition to cores, or this might actually be within a single core, but there's a very small piece of the broader calculator that is like called L1 and L2 cache, which is meant for like super rapid, fast calculations that are even faster than the general compute structure. So, it's possible to like do calculations in the L1 and L2 caches, which get really deep into like computer architecture, and you'll start to get out of my knowledge pretty quickly on them. But again, within a core, you've got a little transistor deeply in the silicon that just like chink, 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 that changes the whole signal throughout the system. Okay, so let's talk about this because this piece is important. ARM and x86. You may have heard there's ARM processors and then there's x86 processors. Most things are x86, like Intel processors, AMD processors, etc. That said, there are also ARM processors, and companies sell them, like a Raspberry Pi would be like an ARM processor. There's also like chips you can buy even for my home-built PC that also have like processors. That actually might be really useful to show right now. I just realized. How do I do this? Stand by 1 second.
I love the look of uncertainty. I'm trying to figure this out.
Yeah, I know. I know. Get it off. All right. I have the case off right now, so this might be a nice little thing to or show you the exact way in which this looks. But sorry, I have too many wires over here. So I'm gonna pull my mic up so you can hear. So this is what every computer looks like on the inside. Just some of the chips are smaller usually. So if I zoom in here, or I come to the side here, the back plane is actually the motherboard. Where's my finger at? Right here. This back plane, this giant chip in the back is the motherboard. And from the motherboard, you plug in all of your peripherals. So just zoom out here for a second. This is a GPU. Usually the GPU is actually just a tiny little chip. It's like about that big inside of this. Most of it's a cooling unit. The CPU is also a small little chip about that big that sits underneath this cooling unit. And then these two sticks right here are RAM. The stick that goes in a laptop is about half the size of this. The sticks that go in big general build PCs are about that big. Then you have, where was the other piece? The M2 drive, which might be kind of hard to see. I think it's behind a plate. It's behind a plate back here, but it's about that big and that round. You can Google them. That's what's in most of the modern CPUs or the modern computers. I wish I had resolution on a camera to actually zoom in and show you the back plane of the motherboard, because it's pretty interesting to see how many different like individual wires you can see zone in, basically not like molded into the actual back plane of the motherboard. broken old motherboards before, and you can see all these little wires. It's kind of really cool. But most of where technology has gone is just shrinking things rather than like progressing in technology. But things like quantum computing are actually like generational leaps ahead and do things in a different way, which we could talk about at some point. So we're close to time. So let me talk a little bit about this line here, and then we'll wrap it up for today. So the difference between an ARM and an x86, even though an ARM is cheaper, is actually what's called single input, single output, and multi-input, multi-output, which is just a fancy way of saying x86 processors can allow for parallel processing, meaning you can put multiple threads of signals in and get multiple threads of signals out. ARMs are so cheap because you can't do that. You only have one input and you have one output. And that will be very important for multi-threading and parallel processing, which are two different techniques that we'll talk about in a little bit, or we'll talk about next time, next Friday, to discuss. And this gets into like efficiencies and how you do like large training for AI and all kinds of stuff. So any questions before we wrap up here?
Don't think I have any off the top of my head. I'm just digesting. My brother has like explained his computer build to me multiple times, so it's like vaguely familiar, but it's helpful to see it like firsthand on yours too.
Yeah, it's just adult Legos.
Really is.
Yeah.
He's tried to convince me for years, and now I'm like, okay, maybe I have a little motive to do it.
Yeah. Go to pcpartpicker.com and it's like literally just tells you what Legos fit together and you can just like purchase them.
Exactly it. Yeah.
But yeah, so we'll get into that, and then we'll start to get more software heavy next time, where we talk about types of languages, networking, web dev, robotics. We might make it down there. Cool.
All right, thank you. This is super helpful.
You bet.
Thank you, sir.
We'll chat soon. See ya.
All right. See ya.